Imagine you're a mathematician in the 16th century and you're tasked to find the dy over dx, or the derivative of a function. How would you go about and do that? Let's take a look at a straight line to begin with. You would take an x value, find the corresponding y value, do it again with a different x value, and use the change in y over change in x formula to find the gradient slash derivative of this line. Over here it's 6 minus 4 over 6 minus 4, which is just 1 over 1, or simply 1. And the change in y over change in x is just dy over dx, as the derivative of this graph is constant. And as you might notice, the graph is just y equals x because the gradient is equal to 1. What if you had a more complicated graph, such as this one? How would you find the derivative of this graph at a certain point? In this case, how would you find the derivative at x equals 1? You might go with the same approach and draw 2 points on the graph, find the gradient of the line between them. But as you can see, the actual gradient's line or tangent is much different to the line we drew. So by intuition, you might bring the other point closer, and as you can see, the two lines get closer. So you bring it closer again, and it gets much closer. And even though 1.035 is very close to 1, the lines are still not equal to each other. So the gradient we find using these 2 points will be an approximation and not the gradient. So let's write this down algebraically. We can say our dy over dx is approximated to f of x plus h minus f of x over h. H is the difference between the two x values. In our case, it was 0.035, and f of x plus h is the y value of the second point, and f of x is the y value of the first point. So f of x plus h, as you can see over here, is equal to 1.109, and f of x is just equal to 1. But this is an approximation. We want to find the actual gradient. For that, we use limits. So we say dy over dx is equal to the limit as h approaches 0 of the equation. What this means is that the gradient is equal to whatever this equation seems to be approaching to as h decreases and decreases approaching 0. So as you can see over here, if we reduce h to 0.016, the gradient is equal to 3.05, and at 0.009 it's equal to 3.022. So you can see it's decreasing and seems to be approaching 3. So the gradient must be 3 at x equals 1. And let's prove this algebraically. We can swap f of x plus h with x plus h cubed, because the graph we had was of x cubed, and f of x could be swapped with x cubed. And then we can expand the left part to get that, expand it further to get that, put it back into the equation. The x cubed terms cancel out, so we end up with 3x squared h plus 3x h squared plus h cubed over h. Then we can cancel out the h's, we end up with this. And then we can just put 0 for h to get 3x squared plus 0 plus 0. So just dy over dx is equal to 3x squared. We couldn't put 0 earlier because we had h in the denominator and we would get undefined. So there you go, dy over dx is equal to 3x squared. If you put x equals 1 in here, we do indeed get 3. So that proves that the gradient at x equals 1 of x cubed is actually 3. And this works for any point on the graph.